This is Dr. GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today, we will discuss design of springs problems. How to solve helical compression springs, we will see in this session. Already in the previous session, we have studied design procedure of springs and how many types of springs are there, and introduction about springs, and some empirical relations also we have seen. So how to apply those empirical relations to given problem? See, the given problem is here, the design a helical compression spring for a maximum load of 1000 Newton. So given type of spring is helical compression spring, and the maximum load is 1000 Newtons. For a deflection of 25 mm, using the value of spring index as 5. So deflection is given, deflection is 25 and the value of spring index is 5. So in this, no need to calculate separately the delta, deflection and spring index. In previous problems, we have calculated the spring index and delta deflection by using empirical relations. So spring index means, already you know, it is the ratio of mean coil diameter to wide diameter. But here directly is given spring index. But we don't know outer diameter of coil and inner diameter of the coil and wide diameter, small d, we don't know. We need to calculate. Okay, we'll see. The maximum permissible shear stress for spring wire is 420 megapascal. The maximum shear stress given 420 megapascal. This one also no need to calculate. The modulus of rigidity 84 kilonewton per mm square. And the wall stress factor is K given 4C minus 1 by 4C minus 4. So if considering it wall stress factor given means it is considering curvature, effect of curvature. If not considering shear curvature of effect, we have to use shear stress factor. The spring index is C. So first of all, for any problem, first we have to write the given data, what he has given and what he has asked, what we are calculating. So what parameters we have to take, the major parameters, and what are the empirical relations are useful for given data. You have to verify. So the given is load is 1000 Newton. This is axial load and delta 25 mm and C 5. So you know the spring index is the ratio of mean coil diameter to wide diameter. So given 5. And shear stress is 420 megapascal. So this is converting to Newton per mm square. So 420 megapascal to 10 to the power of 6 Newton per meter square. And again convert into mm square. So 420 into 10 to the power of 6 by 6, you will get Newton per mm square. So 10 to the power of 6, 10 to the power of 6 get cancelled. So same value will get Newton per mm square. So it means 1 megapascal is equal to 1 Newton per mm square in terms of mm. In term 1 megapascal is equal to 10 to the power 1 pascal is 10 to the power of 6 Newton per meter square in terms of meters. Next, G 84 kilonewton per mm square. So this one convert into Newton per mm square. The kilonewton convert into Newton, 84 into 10 cube. The mean coil diameter. So let us assume D and small d diameter of the spring wire. we know wall stress factor K is equal to 4C minus 1 by 4C minus 4 plus 0.615 by C. So we calculate a wall stress factor K by using spring index. Directly is given spring index. So the maximum shear stress. Now we apply the maximum shear stress formula. What is the empirical relation? Shear stress is equal to wall stress factor into 8WC by 5D square. So you can write in terms of capital D also, WD divided by 5D cube. So we know C is equal to capital D by D. But we can't use this formula. So for WD by D cube. Why? Because we don't know the outer diameter and the mean Y diameter small d we don't know. So that's why directly you can substitute spring index value in this empirical relation. So calculate the wall stress factor 1.31. We calculated or given? Calculated. So 1.31. So calculate and 1.31 you'll get stress factor and then multiply with the given values. 8 into 1000 into 5 divided by pi d square. We will get 16,677 upon d square. In terms of d square, we will get the shear stress. So shear stress value already you know. So equate to shear stress value. So the shear stress is 420. So 420 is equal to 16,677 by d square. So calculate d. So d is 6.3 mm. But your calculated value is 6.3. But always you have to take the standard value from design data book. So what is the standard wire gauge? So the wire diameter, what is the standard value? So the tabular form is available in design data book. You have to verify and take that value as 6.401. This is the standard wire diameter. So now calculate mean coil diameter of the spring. So you know C is equal to capital D by D. So capital D is coil diameter, capital D is C multiplied with D. So here C spring index value, 5 and small d already we calculated here. So take the standard value 6.401. So multiply with, you will get capital D. And then calculate outer diameter of the spring coil. The outer diameter. So how do you calculate the outer diameter? So already in previous sessions we have discussed the outer coil diameter. D naught is equal to capital D plus small d. The outer diameter of the spring coil is equal to the summation of coil diameter, mean coil diameter plus wire diameter. It gives outer diameter of the spring coil. So D, capital D already calculated and then small d also you know. So substitute in this relation, you will get 38.406 mm value. So up to here, you have calculated capital D and the small d and outer diameter of the spring coil and wall stress factor. Now, need to calculate number of turns of the coils, that is n dash, but let n number of active turns of the coil. So number of turns are different, and number of active turns of the coil also different. So while applying load on the spring, some coils are taking load only. So actively participate during deflection. Those coils are called as active coils, active turns. So how many number of active turns are there? You need to calculate. And then number of turns, total turns of the coil. So suppose number of turns are 10 and the active coils are 8. So like this, you have to calculate by using end conditions of the spring. What are the end conditions? Squared and ground end, flat. These type of end conditions are there. The number of turns of the coils depends upon the end conditions of the spring. For squared and ground end, the total number of turns n dash is equal to n plus 2. You have to take from the tabular form. So sometimes in our problem, clearly they will mention this type of spring end shape is squared and grounded. But in this problem, I think not given, but you can assume that for helical compression spring, the end conditions are squared and grounded. Now according to the squared and grounded condition, the n dash is equal to n plus 2. So that is, you will get 16. So n is, and n you have to calculate by using deflection formula. Delta is equal to 8 W C cube n by capital G into D. So deflection value already you know given in the problem, and then W you know and C also given, but only unknown is n. G is modulus of rigidity and D wire diameter. Substitute all those given values in this relation and you will get the number of turns, number of active turns 13.44, you can say 40. So for squared and ground ends, the total number of turns n plus 2, now substitute this value in this relation, you will get 16. Next, find out free length. Free length of the spring. We know that the free length of the spring is, what is the relation? Empirical relation. N dash into D plus deflection plus 0.15 deflection. This is the standard empirical relation. So only we have to substitute the given values in this relation. N dash, the number of turns. In previous step, we have calculated the total number of turns. The total number of turns are 60. Capital D, wide diameter, we have calculated 6.3, but don't substitute 6.3. The standard value you take 6.401. Standard wire diameter plus deflection given 25 and 0.15 multiplied with 25 will get 131.2 mm. So pitch of the coil, we know that the pitch of the coil, need to calculate the pitch of the coil. So the pitch of the coil formula is free length upon free length by n dash minus 1. So free length already calculated here, and n dash we calculated in previous step and substitute those values, you will get 8.75 mm. So this is the free length of the spring. So next problem, design a closed coil helical compression spring. So this one also helical compression spring, but the given type is close coiled. For a service load ranging from 2250 newtons to 2750 newtons. But here the given load is not a constant load, so not given directly as previous problem. Here the range, the service load range is given to 2250 to 2750. So it means the load will be vary minimum to maximum value. The minimum is 2250 and the maximum is 2750. So the axial deflection of the spring for the load range is 6 mm. The deflection is 6 mm. Assume the spring index is 5. In this problem also directly given the spring index. If not available spring index in given problem, you can assume the spring index as for the given material. The permissible shear stress intensity is 420 megapascal. Shear stress and modulus of rigidity also given 84 kilonewton per mm. So neglect the effect of stress concentration. Here don't take effect of stress concentration. If consider stress concentration, what you have to do? You have to multiply the stress concentration factors. So various factors are there: size factor, surface finish factor, reliability factor, temperature factor. All these factors affect the stress concentration. So that is fatigue failure. So here no need to, if considering the stress concentration, so definitely you have to assume some factors and then draw a fully dimensioned sketch of the spring. After completion of design, by using calculated parameters, so draw a fully dimensioned sketch showing details of the finish of the end coils. So end coils also you have to show the shape of the end coils. So how to solve this type of problem we will see. The first step is given data. So given data is the initial load, the minimum load is, let us assume W1 2250 newtons and W2 is 2750 newtons. And the given delta is 6 mm. And C is capital D by D. So spring index, so given value is 5. And shear stress value 420 Newton megapascal. So you can convert into 420 Newton per mm. G is 84 kilonewton per mm. So this one also in terms of mm square, 84 10 cube. 84 10 cube Newton per mm square. So mean diameter of the coil, let us assume capital D for a maximum load of 2750 newtons. Take the maximum load. And D is diameter of the spring wire. So now calculate twisting moment on the spring. How do you calculate the twisting moment? Force multiplied with distance. So with what distance the load is acting? So multiply, you will get twisting moment. So load is 2750 multiply with radius. So that is D by 2. But we don't know the capital D, main diameter of the spring. Only the available parameter is spring index. So that is capital D by D. The spring index is, given spring index is 5. So capital D by D. So that capital D is equal to 5D. You can take in place of capital D, 5D. So you will get 6875 D. In terms of diameter, you will get twisting moment. Now, twisting moment in terms of shear stress, twisting moment is equal to T is equal to 5 by 16 tau into d cube. In shear stress formula, torsion formula, you know that T is equal to 5 by 16 tau into d cube. In this, the T twisting moment already calculated in the previous step, and tau is shear stress given in the problem, and D is mean wide diameter. But we need to calculate the wide diameter. Here unknown is, so this equation are converted into in terms of small d. So here twisting moment in terms of d, and here shear stress given, and finally 82.48 d cube. So equate. So you will get d is equal to 9.13. Here also you have to take the standard spring wide diameter from a design data book. So that is 9.49. So multiply with 5, you will get 47.4 for 500. So next one, you know that outer diameter of the spring coil D naught is equal to capital D plus D. So outer diameter of the coil is equal to summation of mean coil diameter plus wide diameter. So 47.45 plus 9.49. The standard value to substitute here. So we'll get 56.94 mm. So now if you know the outer diameter, and you can calculate inner diameter of the spring coil, Di is equal to capital D minus D. So that is 37.96 mm. Next one, number of turns of the spring coil. So to assume number of active turns N, and it is given that the axial deflection for the load range is 2250 newtons to 2750 newtons. So that is for the load is 500 newtons is 6 mm. So know that the deflection of the spring delta is equal to AW into C cube into N by G into D. So here W, the deflection already given in the problem, and W is the load, and C is the spring index, and N is number of active turns. Need to calculate N. We don't know N. So substitute all given values in this relation. You will get N is equal to 9.5. You can say 10. So in this one also, the end condition shape is squared and grounded. So total number of turns N is equal to N plus 2. For squared and ground ends condition is N plus 2. So N is here active turns are 10 plus 2. You will get total number of turns 12. Calculate free length of the spring. Since the compression produced under 500 newtons is 6 mm. Therefore, the maximum compression produced under the maximum load of delta max is equal to 6 by 500 to 2750. You will get 33 mm. We know that the free length of the spring LF N dash into D into delta max plus 0.15 delta max. To substitute those values in this equation, you will get 151.83. You can say 152 mm. Next, calculate pitch of the coil. So you know pitch of the coil P is equal to free length LF by N dash minus 1. So N dash total number of turns calculated, and here you will get the pitch of the coil is 13.8 mm. So finally, what he has asked, draw the spring with the calculated values, design values. Here, helical spring, the square, the end condition C is squared and ground, type. So the type of the cross section of the spring is here circular one. So capital D is main coil diameter. Inner diameter DI. D naught is outer diameter of the coil. So do you calculate the outer diameter? D naught is equal to capital D plus small d. Main coil diameter plus wire diameter. Similarly, the inner diameter is capital D minus small d. Already we have calculated. And D is the wire diameter. 13.8 mm is pitch of the coil. As per our definition of the pitch, it is the axial distance between two adjacent coils. So that is 13.8 mm. The total length of the spring is 152 mm. So like this, you have to draw spring, helical spring by using the calculated values. These are the references I have taken. B. Bandari, the design of machine elements textbook, and R.S. Kurmi, and R.L. Norton machine design book. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.